Hello everyone. We're starting a free open lecture in our Discord. All our lectures are held weekly without interruptions. If you, the viewer, want to ask questions online and get answers, join our lectures. You can find the link to Discord in our Telegram channel. To find out the schedule for the lectures, join our Telegram channel. Well, accordingly, recurrence relations. Recurrence relations. Overall, we have 4 of them here. So, first one, this is how we calculate dp for the current vertex v. We calculate big sub. For the current vertex, update x and y for its parent. Then update the parent's dp considering the current vertex's dp updated at the end. We update the dp for the parent, taking into account the dp for the current vertex, and this is updated at the end. Once the dp for the vertex is calculated, in Patrick, it's the array length, count n, and the vertex's neighbors. Examine the formula. It's straightforward, but how these elements work is seen in handling dpv, combining x and y. Well, and accordingly, let's say here is count, and yours is the number of neighbors at the vertex in this way. Well, and here in detail, so to speak, we will consider this and this formula. What I have here is nothing complicated either, but how I handle these two things can be looked at in terms of how we work with dpv, where we combine x and y. So what happens between them is that I remembered the same vertex 6, how the answer came out, and why it resulted in 6 in the code, which took about half an hour. And we have some vertex, here it is 6. For it, x and y will be calculated xy, here it will be what it will be. We have big subs from 7 and 10 vertices, meaning that from these two children, we will get maximum big sub, which will give us, if we take the big sub of 2, as we can see, there's a 1 here. If we take big sub, from here it will be zeros, because there's nothing down here, just nothing at all. It will also add Skype to the total, which is the maximum of the number of neighbors for the vertex face minus 2, well, or 0 is added if there's nothing else left. What does that mean? The path goes like this. Through vertex 6, it disappears, and here everything disappears. What will we get here? We'll find out from x and y. And what is located right here? And here we find out exactly from the number of neighbors for vertex v. So for vertex 6, so that's the situation. Here we have, not counting the 7 and 10, 3 neighbors left. This is 1, 8, and 9. And accordingly, in this way, we get the answer 2, plus 1, plus 3. This is how we combine both x and y. Next, in the dp task, if we need to select exactly 2 maximums among the children of vertex b, we're removing these two because they are, for specific reasons, part of x and y still passes like this, and all these 2 neighbors of u are no longer there. So it's minus 2 for the second part of the dp formula, which is similar, considering the second vertex as the subtree root. We choose some path from the current vertex, meaning there will be some big sap. The largest big sap will be x for this vertex, and we find that for vertex 6, the dp will be built. In this case, the largest big sap will be x for this vertex. So we find that for vertex 6, dp will be built. We find the big sap for 7. This is already a known pair. There are no more big saps among the children of 6, and so we add 3. Here it is already subtracted from the number of middle ones, because only the 11th set is removed. And all of these stay with us. Well, that's it. We get here. We sum up the big sap from 7 plus 3, that is 2 plus 3, 5, for dp from 6. With this particular arrangement, the slight difference between these tasks allows everything to be sorted out in the most optimal way. So, ultimately, in essence, the last formula, how the big sap is actually calculated, is as follows. So, we choose x, which was for this vertex, specifically for the first one. Here, x will again be 2. And what do we add the number of neighbors to? Minus 2? What does that mean? Basically, we consider that this neighbor from where we took the big sap is removed, and this neighbor is also removed. Choose one vertex in the subtree. Subtract 2 to show removal, finds remaining components in vertex 1 subtree after choosing, and we immediately consider that something is removed here, so we subtract 2 right away. And this way, we will know. In the subtree with vertex 1, if we have already chosen one vertex, how many connected components will remain specifically in this one? Sub 3 Here, only 4 will remain, so from the big sub, we get 2. From this thing, we also get 2, which means these 2 stay. Well, 2 plus and 4. So that's how this formula is calculated. Well, if we take a closer look at how x and y are updated, we see that our big sub OTV is greater than the best big sub that has already been recorded in the parents. Well, we update, yes, so we get x and y. We pass into x, our new better big sub among the parents and children for p, to y, sending the second one now. Otherwise, we simply choose for yp, maximum from what is already there. Vishanov. Calculation involves determining vertex paths. Paths are passed to the root, maximizing among all TP. This ensures the optimal answer, theoretically accurate. Maybe like this, or at least somewhat like this, but in fact, we just pass it all the way up to the root, taking the maximum among all TP. You will have the exact optimal answer, although in theory, that's actually how it is. The thing could have been not done, and at the end of the pass, select the maximum from all the vertices. But in this case, we just immediately click on our root and find out the answer. Y minus 2 here. We assume that we've chosen one of the 2 nodes between which the entire path is erased. And we assume that the second one will be somewhere up there. And that's why we think that this path continues further up. We will also remove the parent of node 1, so it won't be there either. That's why we are moving away, and this thing is on top, so there is no need to be here. We're urgently working on this, like a paint shop then, when we have chosen somewhere here at the top 2 better big subs, glue them here, somewhere in the middle, like this both of them, and there are still questions. It is noted that the starting value is all filled with zeros, except for big sub, raven. The number of neighbors is -1, y -1. We hit the node, removal starts here and continues there. Rest is zeros. Max should be 6, unsure if right. For DP, it gets filled with the initial number of neighbors. Need max, 6. For DPeshka, the world is filled with initial neighbors. For big sub, better to start removal here and go up. For DP, starting value is removing 1 node, like 6. Output its neighbors count. And for DP, the starting value will be the scenario where we basically just remove this 1 node, like the 6 for example, and that's it. And we output the number of its neighbors. So if we were removing 6 here, the answer would be there. 1, 2, 3, 4, 5. The starting values should be like this. So accordingly, the answer will be in DP start, where start is the root from which the tree is suspended. Well, and the complexity, well, in terms of time, that's the complexity of the traversal, meaning the memory line, you can add a constant, it will be 4 lines, 4 or 5 lines. In any case, it will not be greater than the logarithm, so you can even not specify the constant in particular. There, the limitation allows FSB consulates to increase by tens, at least they will reach 100, 10, 10. In the 7th, we can already have someone, well, what about the cat, it turns out? What do I have here? But I traditionally stuffed it at the beginning of a for tree. The method is stored in the dictionary in such a way that something happens here with the daughter. We're choosing a clear starting point so that the neighbors are more than 1. It's actually surprising, by the way. Why didn't it drop for me? Actually, there's some magic happening here. So they have a leaky Dima, but someone should make the delivery. Actually, what we have here are 2 nodes, and we only have 1s everywhere, and we should go beyond the boundaries to get a goose, but there won't be a goose. In the dictionary, you won't have a dictionary. Someone will need to be here. Actually, what we have here are 2 nodes, and we only have 1s everywhere, and we should go beyond the boundaries to get a goose, but there won't be a goose. Dictionary is obvious. You will not be dictionary. Someone will be needed here. This is an additional check. Lucky to learn, so it means we can do it like this, it turns out, to search.
Want to become a great programmer? Subscribe to our Telegram channel.